Okay. Next, triple integrals in cylindrical and spherical coordinate. Okay. We have done triple integrals in rectangular coordinate before. So now we do the same thing in cylindrical and spherical coordinate. Okay. In cylindrical coordinate, the point x, y, z in rectangular coordinate can be written as r theta g with the relationship of x is equal to r cosine theta, y equal r sine theta, and g is equal to g. So by replacing this in here, we have b tilde as a region, and the x, y, z are replaced like this, and this x, dx, dy, dg replaced by r dr d theta dg. So if we wanna do the triple integral of x square on this the object, then what we supposed to do? Okay. In this case, as you see, this integral involves the square root of 4 minus x squares, so which can be easily transformed to the cylindrical coordinate by this substitution. So in this region can be written as the point x, y, z with the x square plus y square is less than 4 because it's inside of this circle with radius 2, and x square plus y square is less than g is between this function and up to 1 here. Okay. So if we replace this with if the x, y, z are replaced by r cosine theta, r sine theta, and g, then this can be written in this way, because the radius are bigger than or equal to 0 and less than 2, and theta is a whole 2 pi, and g is from here. This one is r square n square, so r to the fourth is from 1. So this domain can be represented in cylindrical coordinate in this way. So we just do the integration x square on these intervals. Here r dr d theta dg comes here, and x square is r square times cosine square square. So cosine square theta r cube dr dg d theta, and here g has a variables interval, so we do the integration for g first, and then the r and theta has the constant integral interval, so that the orders doesn't matter. So we do the integration for r next, and the integration for theta at the last. Then this can be integrated in this way, and this simple integration gives us minus 28 times integral from 0 to 2 pi cosine square theta d theta, which is minus 28 pi. That's the integration of x square on this, in this region. Next, find the volume V of the solid bounded by a spherical surface. This is the first octant of the sphere with radius 2. And the cylinder R is equal to 2 sine theta, and it has an intersection like this. So we are looking for the volume of the solid in here. We are looking for this one. And 8 times of it. Okay. Since the bounded solid can be written in cylindrical coordinate like this, so R is between from 0, it moves from 0 to 2 sine theta, and thetas are from 0 to pi, and then twice of it, and 8 of it. we integrate it from 0 to pi, and then multiply 1, 2, 3, 4, 4 of them. Okay, and G we use to find the integral interval. We use this equation. So G square is equal to 4 minus x square minus y square, which becomes this interval. So G is in here, and R is in here, and theta, we use the theta from 0 to pi, and then multiply 4 times, because we have a bottom and all the tops. Okay, so this integration can be written in this way. Here, the volumes like this. So just one here. So dx dy dg becomes r dr dg d theta, and 4 times from 0, the theta is from 0 to pi. And r from 0 to 2 sine theta, and g is between from 0 to square root of 4 minus r square. So, okay, now we cleared up what integrals we should do. Since we are looking for the volume of the intersection between this pair and this cylinder, so we have only 4 of these pieces here and back and bottoms. So we do the integration from 0 to, so we just find this piece, the volume of this piece first, and just multiply 4 of them. That's what we need. In order to find the volume of this one, we do integrate the one from 0 to pi over 2, and g should be between 0 to this square root of 4 minus r square. So clearly, the volume can be obtained 4 times this object. This object is obtained, the integration, by dr dg d theta, which is the interpretation of dx dy dg, and one is here, and g should be between from 0 to square root of 4 minus r square. That's done. And r from 0 to 2 sine theta, and theta from this first octant from 0 to pi over 2. So this is what we have. If we simplify this, then it can be written in this way. In order to have the integration of this one, we do substitute this 4 minus r square as t, then r dr d theta can be written as minus 1/2 dt, because dt is equal to minus 2 r dr, and this gives us this. And in this substitution, x is equal to 0 means t is equal to 4, and x is equal to sine theta means t is equal to 4 cosine square theta. So this substitution gives us this integral from with respect to t and theta, and with this integral and so this can be easily computed to have this. That's it. 4/3 times 4 pi minus 16 over 3. Next, substitution to spherical coordinate. So now we have the same thing. If we wanna have the spherical coordinate of a point in rectangular coordinate, then this x, y, g are replaced by this. When rho is greater than or equal to 0 and theta is between 0 to 2 pi and pi is between 0 to pi. The area element dx dy dg are replaced as rho square sine pi d rho d theta and d phi. That's what, as we see. And so this integral can be rewritten in this way. Next example is to evaluate this integral, where b is written given in this way. If we substitute it with this spherical coordinate, you see? Okay. Yeah, this example, yeah, in this case, yeah, we could handle this triple integral by cylindrical coordinate. So the r cosine theta and r sine theta replacement gives us this, which is also a simple integration, which can be computed to get pi over 2 times e minus 1. So this one was an example of the cylindrical coordinate transformation case. And the next theorem, the next example shows the spherical coordinate examples. Here, find the volume of a sphere with radius a. Okay. This sphere can be described in a spherical coordinate like this, because this radius, this is rho square. So rho square is less than or equal to a square. So rho should be between 0 to a. So radius starts from 0 to a, and then we draw a circle of radius with the half circle first, and then rotate into from 0 to 2 pi to have a whole sphere. So this is the right presentation of this sphere. Then all we have to do is this sphere can be obtained as a triple integral on 1 and dx dy dg, which can be replaced in this way, and rho from 0 to a, pi from 0 to pi, and theta from 0 to 2 pi. This is a simple integration that can be done by hand or by using the CAS tool. And find the volume of the solid enclosed by the spherical surface x squared plus y squared plus g squared is equal to 9, and the cone g is equal to square root of x squared plus y squared. And this is what we are thinking. And this is a sphere, and this is a cone, and we are looking for the region here. Okay, the volume here. So this also can be drawn in this way by Sage, and this can be written as what? Radius rho is from 0 to 3. This is 3 square, and theta from this is a half. So we draw. We only have this on the above the xy plane. So we do rho should be between 0 and pi over 4, and then rotate it to 2 pi. Here, because of the substitution, this rho radius is from 0 to 3, and this pi moves from 0 to pi over 4 like this, and then we rotate it with the theta direction to whole circle 2 pi. So we have this region. That's why we have triple integral from 0 to 2 pi and 0 to 4 pi over 4, and from 0 to 3 with dx dy dg, which is rho square sine pi, d rho, d theta, and d pi and d theta. This becomes this one, and which is this, and then just the simple integration gives us 9 pi times 2 minus the square root of 2. Okay, all these substitutions comes from this substitution from rectangular coordinate to the spherical coordinates. So the essence of this substitution is this xyz coordinate of the whole three-dimensional space can be represented as rho as a radius from 0 to above, and theta from one direction from here to here to here, from 0 to pi over 4, pi over 2, and pi, and theta and pi and pi from here to here, and theta from the whole circle like this. That's why they write rho and theta and pi in this way to cover whole three-dimensional spaces. I think that's it for the section 14.6, and these are the examples and solutions that you can deal with, and that you can actually see how these integrals and the intersections and the volumes, what you are looking for. Okay, any questions before the last section in chapter 14?